Hello. In this module, we will go deeper into naming other hydrocarbons as well as naming haloalkanes. As always, please read Chapter 12 of our textbook for a more in-depth discussion of the topics covered here. Slide 2. Intended learning outcomes. At the end of this module, the student must be able to successfully demonstrate the following learning outcomes. 1. Give examples of haloalkanes. 2. Know the sources of hydrocarbons. 3. Differentiate alkenes and alkynes. 4. Give the names of simple alkenes and alkynes. 5. Draw some simple structures of alkenes and alkynes. 6. Identify some common terpenes. Slide 3. Haloalkanes. Haloalkanes, also called halogenated alkanes or alkyl halides, are alkanes with a halogen atom, fluorine, chlorine, bromine, or iodine, replacing one or more of the hydrogen atoms. Slide 4. Naming haloalkanes. The rules for naming haloalkanes are pretty much the same as for naming any alkane or cycloalkane. The only difference is that haloalkanes contain a halogen substituent. For the substituent, use the names fluoro, chloro, bromo, and iodo. Slide 5. Example 1, naming haloalkanes. As an example, consider the following molecule. This compound is an example of the class of compounds called chlorofluorocarbons. These compounds were once commonly used in refrigerators, but their use is now discontinued as overwhelming scientific evidence shows that chlorofluorocarbons destroy the ozone in the ozone layer of the atmosphere, producing the ozone hole. This ozone hole lets in harmful UV radiation that causes damage to living cells. In this example, we see that the parent chain has 2 carbons. Thus the parent's name is ethane. There are 4 fluorine atoms, 3 are at C1 and 1 is at C2. Therefore, this compound is called 1112 tetrafluoroethane. Slide 6. Some alkenes in nature. In this module, we will focus mostly on alkenes, as they are the more abundant class of compounds in living systems. Alkenes are quite common in nature. Ethene, also called ethylene, is a compound plants produce to stimulate ripening of fruits. Limonene is responsible for the bright smell of oranges and lemons. Lycopene is a more complex alkene that is responsible for the reddish-orange color of tomatoes, and is an antioxidant that possibly lowers the risk of cancer and cardiovascular disease in humans. Slide 7. Classes of hydrocarbons. As was discussed in our previous modules, hydrocarbons may be classified as alkanes, alkenes, alkynes, or arones. Alkenes are characterized by having one or more carbon-carbon double bonds. Alkynes possess at least one carbon-carbon triple bond. Shown at the bottom are some examples of alkenes and alkynes. Ethylene is the simplest alkene, while ethene, or acetylene as it is commonly called, is the simplest alkyne. Slide 8. What are the structures of alkenes and alkynes? In week 1, we discussed that single bonds are arranged about carbon in a tetrahedron, with an angle of 109.5 degrees. In alkenes, the presence of the carbon-carbon double bond increases the angle between bonds to about 120 degrees. Shown here are 2 examples of alkenes. If you count the number of carbon atoms and hydrogen atoms in these, you might observe that alkenes have the general molecular formula CnH2n. This is the same as for cycloalkanes. In fact, cycloalkanes and alkenes are constitutional isomers. Recall from week 1 that we defined constitutional isomers as compounds with the same molecular formula but different arrangement of atoms. Slide 9. What are the structures of alkenes and alkynes? In alkynes, the bonds about each carbon in the triple bond are about 180 degrees. Alkynes have the general formula CnH2n-2. In ethylene, the 2 carbons of the double bond and the 4 hydrogens bonded to them all lie in the same plane. In contrast to methane, where the bonds are oriented in a pyramid shape in space. Meanwhile, for acetylene, the atoms in the molecule all lie in a straight line. Slide 10. Cis-trans isomerism in alkenes. In week 1 we discussed cis-trans isomerism in cycloalkanes. We know that this arises because the orientation of substituents in space may differ. If the substituents are on the same side of the ring, the isomer is cis. If they are on opposite sides, the isomer is trans. A similar idea is true for cis-trans isomerism in alkenes. This type of isomerism exists when there are 2 substituents, one on each carbon in the double bond. Shown here is cis-2-butene and trans-2-butene. In the cis isomer on the left, the carbons in the parent chain all lie on the same side of the double bond. If the carbons in the parent do not all lie on the same side of the double bond, like on the right, the isomer is trans. Cis-trans isomerism is particularly important when talking about fatty acids. You might have seen foodstuffs with the label no trans fat. Fatty acids have an alkene tail and a water-soluble head. Trans fatty acids have kinks in their tails, because of how the substituents in the alkene are oriented in space. Trans fatty acids are responsible for raising the amount of bad cholesterol in your blood, while lowering your good cholesterol. Slide 11. Naming alkenes and alkynes. To name alkenes and alkynes, we follow the following rules. 1. Find the longest carbon chain that includes the double bond or triple bond. Indicate the length of the parent chain by using the stem that tells the number of carbon atoms in it. Note that the longest chain may not necessarily contain the double bond or triple bond. In this case, the longest chain may not be the parent chain, as is the case for alkanes. 2. To the stem, add the suffix ene for alkenes, and yne for alkynes. 3. Number the chain from the end that gives the lower set of numbers to the carbon atoms of the double bond or triple bond. The double bond and triple bond always gets prioritized in numbering over all other substituents. 4. Branched alkenes and alkynes are named in a manner similar to alkanes. Substituent groups are located and named. 5. For alkenes only, where appropriate, use the designation cis or trans to distinguish between isomers. Alkynes do not exhibit cis-trans isomerism. Slide 12. Example 1, Naming alkenes. Let's start with a simple example. In this molecule, the parent chain is named hexene, hex because there are 6 carbons in the parent chain, and ene because it contains a carbon-carbon double bond. We then assign the locants such that the double bond gets the lowest possible number. By numbering the carbons in the parent chain from right to left, we see that the double bond is at C1. Thus this compound is called 1-hexene. Slide 13. Example 2, Naming alkenes. As with our previous example, we count the number of carbons in the longest chain in the compound that contains the double bond. Since there are 6 carbons in the parent chain, the parent is hexene. Next, we count off the carbons in the parent from right to left, so that the double bond gets the smallest possible number. The double bond is therefore at C1. Thus the complete name of the parent is 1-hexene. The parent chain has one methyl group at C4. Thus the name of the compound is 4-methyl-1-hexene. Slide 14. Example 3, Naming alkenes. If we look carefully at the condensed structural formula of this compound, you might notice that the longest chain in the molecule has 6 carbons, numbered in blue. However, this is not the parent. This is because this chain does not contain the carbon-carbon double bond. An alternative chain, numbered in pink, has only 5 carbons but contains the double bond. This second chain is the parent chain. The name of this parent chain is 1-pentene. Now that we've identified the parent chain, we can see that it has 2 ethyl groups attached to it, one at C2 and another at C3. Thus, the complete name of this compound is 2,3-diethyl 1-pentene. Slide 15. Example 4, naming alkenes. Looking carefully at the formulas, we see that the longest chain containing the double bond has 5 carbons. So that the double bond gets the smallest possible locant, this structure is numbered from left to right. That way, we see that the double bond is at C2. Thus the name of the parent chain is 2-pentene. There are 2 methyl groups attached to the parent chain, one at C3 and another at C4. Adding the names of the substituents, this compound can be called 3,4-dimethyl 2-pentene. Finally, looking at the condensed structural formula, we see that the carbons in the parent chain all lie on one side of the double bond. This is highlighted in the purple box. All of the carbons in the parent chain are inside this box. Since they are all on the same side, the alkene is its cis isomer. Thus the complete name is cis-3,4-dimethyl 2-pentene. Slide 16. Cycloalkenes and dienes. A cycloalkene is an alkene that contains carbon atoms joined to form a ring. Dienes are alkenes with 2 carbon-carbon double bonds. An alkene may have more than 2 carbon-carbon double bonds. An alkene with 3 double bonds is a triene. In general, alkenes with more than 1 carbon-carbon double bond is called a polyene. An example of a molecule containing a cycloalkene is limonene, as we saw in slide 6. Lycopene is an example of a polyene. Even though cycloalkenes and polyenes are numerous in living systems, we will skip over their naming in this module. This is simply for the purpose of keeping the discussion as simple as possible. Of course, if you are interested, you can read more on the topic in the textbook. Slide 17. Terpenes. Terpenes constitute what is arguably the largest and most diverse class of natural products. Terpenes may be considered to be made up of isoprene, more accurately isopentane, units. For example, limonene, which is shown on the bottom right, contains 2 isoprene units. Terpenes can be found in many plant sources, while larger and more complex terpenes can be found in animals. For example, rubber is an example of a complex terpene. Slide 18. To summarize, here are the main points covered in this module. Alkenes have at least 1 carbon-carbon double bond. Alkenes have the general molecular formula CnH2n. The bonds about the carbon-carbon double bond of an alkene have a bond angle of 120 degrees, and lie in a flat plane. Alkenes exhibit cis-trans isomerism. The carbon-carbon double bond is prioritized when naming alkenes. Slide 19. As always, please read Chapter 12 of the textbook for a more comprehensive discussion on the topics covered in this module. That's all for this module. See you on the next one.